Hello, everyone. So welcome to the part one of CUDA to SYCL migration. So most of you, I think, have attended the webinar last month, and starting this month, we will be starting more of a hands-on workshop on CUDA to SYCL migration. So this is part one of the series. So let's look at what we will be seeing in the workshops. So February 15th, that is today. So mainly today, we will go over the introduction to using the SYCLomatic tool. So this is the tool that is used to migrate CUDA to SYCL. And then we will also look at how to, once the code is migrated to SYCL, we will compile and execute on the Intel dev cloud on various Intel CPUs and GPUs. And we can also compile it on NVIDIA GPU as well. Right. So next month we will, once we have learned about SYCLomatic tool, next month we will start migrating more complex CUDA projects and look at the challenges we face during migration and how that all works. And then finally, the third part on April 12th will be a mini hackathon and more of a Q&A. So this is more of an opportunity for you to come to the workshop with your own CUDA code that you want to migrate and then have any questions, right? And then we will also, do a recap of SYCLomatic and the migration process, and then give a quick overview of tips and tricks and limitations of the tool and so on, right? So more detailed agenda. What we will be doing today is mainly introduction to SYCLomatic tool and compiling, executing SYCL code on Intel dev cloud. So the first thing we will be doing today is installing the SYCLomatic tool on your CUDA development machine. And then we will understand how the SYCLomatic tool can be used, different command line options. Then we will start off by migrating a very simple CUDA source, right? Just to understand how the tool works. And then we will compare the CUDA source with the migrated SYCL code and understand how the mapping actually works. And then we will also, pull down a CUDA project from NVIDIA's CUDA sample repository and then try to migrate one of the examples there, right? So mainly at the end of this session, you will understand how migration works. Mainly, we will look at how memory allocation and memory copy is accomplished in CUDA versus SYCL. And we will also look at how a kernel is offloaded to run on a GPU on CUDA versus SYCL, right? So that will be the main learning objective of this session. And then coming up in the next session, like I mentioned, next month, we will be migrating a more complex CUDA source with SYCLomatic tool. So in this workshop, you will end up learning more CUDA features like local memory, cooperative groups, work primitives, atomic operations, right? So we will pick a project that has all these CUDA features and then try to migrate it to SYCL using the tool, right? And we'll understand how the features actually map. And then finally, the third session in April, it will be more of a hackathon. We will have some Intel experts to help you answer or help with any of the migration process that you're already working on. We will also give an overview of the tips and tricks, and also look at how libraries like cuBLAS and cuFFT can be migrated in your project, right? So that is the main agenda coming up. So I think this was mentioned in the agenda, in the signups for this series, that the main prerequisites for this workshop is that we require you to have a CUDA development machine, right? So the system which already has CUDA SDK installed, and then something that you're using to compile and run your CUDA sample code, right? So this is mainly recommended so that you can follow along as I'm doing the workshop. So if you don't have a CUDA machine, you don't have to worry about it. You can just watch the session, and it's just one command that will be running to actually migrate the code, right? And then once it's migrated, we will we can take the migrated code over to the Intel Developer Cloud, and then we will look at how to compile the migrated SYCL code. Right? So to do the second part, you'll have to sign for a Intel Developer Cloud account, right? If you don't want to use the Developer Cloud, then you can actually use one of your own bare metal system, which has a CPU and GPU, right? So that's mainly the prerequisite. So with that, let me start with the workshop. To start off with, what I'm going to present here is, so I have my, the black screen that you see here is my CUDA development machine, right? So this machine that I have here, it has a NVIDIA card and it has a CUDA SDK installed. So the way I check that is I just do a NVIDIA SMI to show what kind of system I have. So I have a CUDA 11.8 installed, and then I have a Tesla P100 card in the system, right? So if I do a CL info, for example, you can see that this machine has a Intel Xeon processor. It has an NVIDIA card, right? And then it also has this Intel FPGA emulation device, right? So this is my hardware configuration. So the one thing you have to do on this system is that you'll have to install the SYCLomatic tool, right? So let's look at what is SYCLomatic. So if you just Google SYCLomatic, you will end up at this GitHub page, right? So this is the open source project for SYCLomatic tool. So all the source code is here, and there's documentation on how to build this tool, right? So you can either pull down the source and then build the tool, or this project actually builds a nightly build, so we can just pick the build binaries, right? To get the binaries, what we have to do is go into tags, and then click on releases, and then you can see that almost every day we have a build being generated. So if you pull down the assets here, you'll see that there is a zip file for Linux, there's one for Windows, and then also there's the source code if you want to build it by yourself, right? So for today's session, what we will do is just pull down this zip, right? This compressed package here for Linux. So what we will do is so there's one every day. So the last one that I tested was, I think, February 6th. So I'll scroll down and then pick that one because I know it's a good working version. So you can do the same thing. If you have a CUDA development machine, you can follow along. So what I'll do is just right click on this package, and then I'll copy the link address, right? So this is, we'll download this file. So now I'll go back to my CUDA development machine. So I'm in my root folder right now, right? So what I'll do is I'll create a folder called SYCLomatic, KDIR. Right, so I'll create a folder, and then I'll get into that folder, right? And then let's look at where I am. So I'm in my home folder, and I created a folder called SYCLomatic, and we'll download the package here. So I'll just do a wget and then paste the GitHub link to the compressed folder here. So once I hit enter, you can see that it downloaded the Linux _ release. So if you're seeing any issues with wget, it's most probably like your proxy issue. So next, what we will do is, even though we call this a SYCLomatic installation, it's not really installing anything on your system. We're just unpacking a bunch of files, right? So if you're kind of paranoid like me, who doesn't want to install anything on your development machine, this is kind of good news, because the whole tool is available as just a bunch of files, and we'll just be accessing some binaries from that, right? So what we'll do is just unpack this thing. So just do a tar XVF, and then the package name. Right, you can see that it just unpacked the file. So it's the whole tool is only about 22 megabytes, as you can see. So if you just look at all the different files directories it created, you can see that it created a bin, some extensions include file, library files, right? That's all. So if you look at the bin folder, you can see that there's a bunch of binaries here. DPCT, intercept build. So these are the binaries we will be accessing to do the migration process. C2S. So this is the main tool that we will be using in command line, right? So we will be using this path from wherever your CUDA source is. So it's to make it easy, it's recommended to just add this SYCLomatic bin path into your path, right? So we can do like an export export path equal to this one, right? So and then we can just put the entire path, which is home. In your case, you can put your username, or it doesn't have to be in the home folder. You can put it any directory you want. You just need to set the correct user path, right? So, and then don't forget to include the entire path /bin, right? So this will just make it easy for you to access these binaries, right? So once you've done that, so your installation is complete now, right? So if you want to check your installation, all you have to do is like just do C2S -- version, right? And then it will give you the version number. So if you're at this point, that means your installation is good. So all you've done is like grab the zip package and then unzipped it into a folder called SYCLomatic, and then you added the bin path to your path, right? So if you want to see more how this tool can be used, so all you have to do is like just do C2S and then just do the help, and then it gives you all the command line options. So we will go over how to use the tool. So once you've done this one, right? So once you've installed the tool, the next step is for us to get a CUDA sample code that we can actually try it out, right? So to do that, so what I'll do is like, let's see. So I'll put a link to a simple, very simple CUDA code. So you can copy this code into your CUDA development machine. Okay, so let me paste this link here, right? So hopefully you can access this link, and then at this link, you can see this very simple CUDA code. So let's look at this code, right? So what this code is doing is that you can see that we are including the CUDA.h header file. And then let's jump into the main. You can see that it defines 3 arrays, right? A, B, and C. So A and B are initialized with 1s and 2s, and then C is initialized to 0. And then we are doing some allocation on the GPU memory. For that, we are using CUDA malloc, right, for A, B, and C. And then what we are doing is we are actually copying contents of A and B into device memory, right? So that's what CUDA memcopy does. And once that is done, we are actually executing this kernel function, which is called vector add kernel. And if you look at vector add, what it's doing is C equal to A plus B, and we are using the thread index to actually do parallel processing, right? And all it's doing is C equal to A plus B, so the answer should be 2 plus 1 is 3, right? And then once that kernel is completed, we actually copy back the resulting C to the host, and then we print out the results on the host, and then we free the allocation. So it's a very simple hello world in CUDA. So this is the code we will be copying into the CUDA development machine. So let me do that. So I've created a folder called test, and then you can see that I have already copied this source into a file called test.cu. So if you want to look at test.cu, just go into my editor, and you can see that I have the same code here. So simple vector add code. So before we do any migration, right? So let's see whether this code actually works on the NVIDIA machine, right? So let's compile this CUDA code. So for that, we'll do nvcc test.cu, right? And the compile is done. And then if you run the file, you can see that we get the output 2 + 1 = 3, an array of 16 elements, right? So we can see that this code is actually working when compiled with the CUDA compiler, and it runs on the NVIDIA GPU, right? So once we are at this point, now we can actually start the migration. So how do we do the migration? So it's very simple. So the binary to actually do the migration is just C2S, mainly I think C2S stands for CUDA to SYCL, right? You just do C2S and then specify the CUDA file, test.cu, right? That's it. So if you just hit enter, you'll see that the tool, it's doing migration. It's giving you some data about saying that it created a folder called dpct output, and then it migrated this file, test.cu, right? It processed this one, and then it says that one file was processed. So if you just list the contents of this directory now, you will see that there is a new folder created, dpct output, right? So let's go into that folder, and let's look at what's inside of dpct output. You'll see that there is a YAML file, and then there's a test.dp.cpp, right? So whatever is the name of the CUDA file, so a corresponding dp.cpp file is created. So now this is your SYCL source that is automatically migrated for you. So we can look at that one. Right, so if you look at this code, you can see that all the CUDA headers have been changed, right? So instead of having the CUDA.h, include CUDA.h, it's replaced with SYCL.hpp. So that's how you write a SYCL application. And then if you look at the main code here, right? So here you can see that there is a SYCL queue that is created. The definition of the 3 arrays are the same because it's just C code. And then allocating memory on the device. So instead of using CUDA malloc, now it's being migrated to SYCL malloc_device for A, B, and C. Right. And then you can see that the same way as the CUDA source was doing, now we are doing a mem copy to copy A and B. And then the task is submitted to the device to do the calculation, and there's some commands, right? Like q.parallel4 that's being used, and a bunch of parameters here. And then finally inside that we have the actual function which does the work of adding C = A + B, right? And then the rest of the code, again, it's similar to how CUDA does it. We have a mem copy to copy back the results, and then finally we print out the result, and then there's a SYCL free to free the allocation, right? So if we actually compare this side by side, right? So we had the CUDA code on the left here, and then you can see the SYCL code, right? So you can see, definitely see most of the code, yeah, the C code will remain the same. It's just the CUDA specific APIs are being migrated to, instead of using CUDA malloc here, now we have a malloc_device, right? Instead of using CUDA mem copy, now we have the q.mem copy. And then the way we call the actual kernel function in CUDA, you can see that we specified this total number of elements and then number of blocks. Similar to that in SYCL, we actually use this ndRange class to actually specify the size of each work group and then the total size, right? So in this case, it's just one work group, which is the size of the entire global size. And then we call the actual function. If you want to look at the actual kernel function in CUDA, you can see that C equal to A plus B, we are actually using the thread index.x to actually go through all the elements. And in case of SYCL, we're using the work item, right? The item dot get local ID, right? So local ID is how it indexes to each one of the elements. So you can see that with just one command, we are actually migrated the entire CUDA source into SYCL, right? So hopefully, I think at least a few people are trying this out on their CUDA machines. So please post any questions you may have, or also just speak up on the, speak up and let us know if you have any questions or want me to go much slower, right? So once we've migrated this one, right? So now your job is actually done on the CUDA development machine. So now this code can be taken anywhere else. So it's this code is not just locked to your NVIDIA machine. Now you can actually run this on any Intel CPU, GPU. You can actually run it right on NVIDIA GPU or an AMD GPU or wherever. Right? So that's what is the main advantage of migrating to SYCL. Now this code can be compiled and run on any device, not just one vendor, right? So let me close this file, right? So if you want to compile this migrated code on NVIDIA machine, so you do have to install the SYCL compiler, right? So which you may not have on this machine. I have actually installed that, so I can quickly show you that the code can be run on the NVIDIA machine, either on, because we have an Intel processor here. We also have an NVIDIA GPU. So this code can actually run on either one of those devices, right? So to actually install the compiler, so there is a documentation website that I can actually paste it in chat, right? So you can use that to refer to that in case you want to install the SYCL compiler and then enable compiling for NVIDIA targets, right? So it's mainly an article by CodePlay. So CodePlay has created a NVIDIA GPU plugin for One API. So if you've installed the One API C++ SYCL compiler, you can actually install this NVIDIA plugin, and now you can build any SYCL code to run on either Intel devices or on NVIDIA devices. So let me paste this link for your reference in case if people want to try installing the SYCL compiler on your CUDA development machine. This is a good document. It gives you step-by-step how to get the compiler from Intel website, and then it also gives you details about how to get the NVIDIA plugin and install that, right? So so you can use this as reference. So let me jump back to my terminal here, right? So once you have this SYCL code, so the way we compile this one is just use the Intel One API C++ TP C++ compiler, right? So we use ICPX, and to compile any SYCL code, we use the fsycl flag, and then just the CPP file, right? So let's try this one. You can see that it's compiling. And then if you see, it's created a.out. So I'll just run a.out. And then you can see that we are getting the same output, right? 333. So how do we know which device this was actually run on, right? So if you want to check that, you might have to add a single line of code, which actually prints out the device, right? You can see that in SYCL, when we create a queue, it's associated with the device, and we can actually print out which device it's actually running on. So we'll just do a cout. Let's call it device, and then In this case, we have created a queue called C_CQ_CT1 get device dot get info. Let's put a line break in there, and then we need to specify what do we want to print out, the device name, right? So we'll just put SYCL info device and name, right? So hopefully, just checking the syntax. So this looks good. So now we should be able to compile this again. And then hopefully this will print out which device the code is running on. Right, so if we run the file now, you can see that it prints out the device name. So right now it's saying that it's running on the Xeon CPU, right? The actual kernel code was actually executed and then computed on the Intel Xeon, right? So by default, if you use the ICPX, which is the Intel compiler, it sets the target to Intel devices. So right now we only have an Intel CPU on this machine. So that's what we looked at. If you do CL info -L, you can see that we have a FPGA emulation device, we have a Intel Xeon CPU, and then we have a NVIDIA GPU, right? So let's say you want to run the same code on NVIDIA GPU. So how do we do that? So for that is what you have to install the CodePlay plugin, the documentation, which I just pasted, right? So to compile that, we'll have to include one extra parameter, and we'll have to use the CLang compiler, right? So the way we do this one is we do clang ++ and then SYCL again. And then we have to add another parameter saying that the SYCL target is NVIDIA, right? So let me copy that command. I have it pasted somewhere here. Right. So you do SYCL, that's mainly telling that the code you're compiling is a SYCL code. And then we specify the SYCL target and then specifying that it's NVIDIA CUDA, right? And then you specify the actual C file. So, and then if you compile this one, okay, so it's done compiling. So now if you run a.out, it should actually run on the NVIDIA GPU, right? So now you can see that code which was only capable of running on NVIDIA GPU, once you migrate it to SYCL, you can run it on NVIDIA GPU as well as on Intel CPUs, right? So if you want to try compiling this file on other Intel CPUs and GPUs, we can switch over to the Intel Dev Cloud, and then we can try this code out there, right? So let's do that. So what I'll do is now I'll switch over to Intel Dev Cloud, how to set up that. So hopefully people have signed up for a Dev Cloud account. If not, this is the link. You can actually register right now. It takes about a minute or so to just fill out your first name, last name, email, and confirm your email, and you'll have a Dev Cloud account, right? So let me paste this link here for people who haven't signed up for Intel Dev Cloud. So go ahead and then sign up and sign in. So once you've signed in, there is an option called Get Started. And then one of the ways you can use Dev Cloud is you can just log in using a terminal using SSH, or you can actually access your system using Jupyter Lab interface, right? So that's what we will be doing. So there's an option to launch Jupyter Lab if you go to devcloud.intel.com/oneAPI, get started, right? This is after you logged into your account. Then you click on Launch Jupyter, and this should launch your Jupyter interface, which will look something like this, right? So let me know if people are still trying to sign in, or I can give you some time. If not, I can get started with using the Intel Dev Cloud. So hopefully people are at this point where they've launched their Jupyter Lab interface of Dev Cloud, right? So what mainly this interface allows you to do is it gives you access to a terminal window. So it's same as your local terminal windows. So you're logged in to your Dev Cloud machine. You're on a node, and you can check what files you have, right? So mainly it comes pre-populated with a bunch of folders in your home directory. So these are all trainings that are available that you can that is used to self-learn different topics, right? So starting with One API basics, SYCL programming, OpenMP programming, and so on, right? So you can use this for training, or you can write your own code and then compile your code like SYCL code. So the main advantage of using this Dev Cloud is that you'll have access to a lot of different Intel GPUs, CPUs, and all the tools are already pre-installed. So you don't have to install the compilers or environment variables. Everything is set up. So you can directly get your code and then get going on here, right? So what we'll do on the Intel Dev Cloud now is the code that we just migrated on the CUDA open machine. So we'll get that code over to this Intel Dev Cloud, and then we can compile it, right? So either you can, just get this code, test.dp.cpp, over to your Dev Cloud. So the way you do it is whatever system you have, download it to your machine, just drag and drop it into one of the folders here, right? Or create a new folder, and then you can just drag and drop it here, or you can copy the code and then paste it into a file as well, right? So what you can do here is, so all the migrated code, we've already put it in a directory here, so you can actually copy the tutorial files over to your system. Let me paste the command here to do that. So go to the chat window. So once you're in the terminal in your home directory, you can paste this command. So what this will do is it's just copying a folder called CUDA SYCL migration into your home folder. So we have a master copy of this tutorial. So we're just copying that to your home folder. So I'll just paste this command here. And then if you run this command, this should copy a folder called CUDA to SYCL migration. You can see that this folder right here was just created seconds ago, right? So if you go into this folder, you'll see that we have 4 different modules here, starting with introduction. If you go into introduction, this will give you, there's a Jupyter notebook file here. You click on that. It just gives you SYCL migration introduction. It gives you an overview of CUDA versus SYCL program structure, how the execution model works between CUDA versus SYCL. And then we have a SYCLomatic tool introduction, which we just went over, how to use it and how the migration works and all the different command line options, right? This is just for your reference, for you to self-learn about this tool and then start migrating. And then the second module here, we have the simple vector add example, right? So if you open this example, you can see that there are different folders. You can see that I have a CUDA folder, and then this is the code that we used for migration, right? So the same CUDA code. And then there's also a folder called dpct output. So the output of the SYCLomatic tool is also right here. So if you don't want to copy it from your CUDA machine over here, if it's a long process, you can just use this file here, right? So we already have a migrated file here. So you can use any of this if you want to follow the tutorial of how the process of migrating this simple vector add. You can use this notebook here. It will give you step-by-step instruction explaining what the CUDA code is doing, right? And then what is the process to migrate the CUDA source to SYCL source. It's giving you instruction which I just shared, how to install SYCLomatic, and then the command that is used to migrate, right? And then once you migrated it, you can view the SYCL code and then compile it, right? So this is mainly a tutorial file for your reference if you want to learn it on your own. But then if you just want to try it, try compiling it for different GPUs and CPUs, you can try it from command line right here, right? So hopefully by this point, people are logged into the dev cloud and then run this command, right? So once you've run this command, we can try out compiling and executing the SYCL code. So let's go into the CUDA to SYCL migration folder. Let me check what's in this folder. So we have the 4 modules. So we will go into this directory 01, right? And then you can see that in this folder, we have a CUDA folder, and then we have the DPCT output, right? So DPCT output is the folder that is created by default when you're migrating using SYCLomatic tool, right? So that's what has the migrated code. So let's go into that folder, DPCT output, and you can see that we have a vector add dp.cpp, right? So we can directly compile this and then check the results. So let's do ictx f SYCL and then vector add.cpp. Yeah, so it's compiled, and if we check the directory, it has a a.out output file. So let's check that. You can see that we see the output, right? So again, in this file, let's add the one line that we added in the other example where we print out the device that it's actually running on. To do that, so you can either use your VI editor right in this terminal, or you can actually use, just double click on this file, and you can actually edit this file right here. Okay. So let me add that command again. I'll paste this in the chat window as well. What we're doing is printing out the device name. So we'll do q_ct1 dot get device dot get info. Line break. And then the actual property we are trying to print out is SYCL device info and name. Right, and I'll save this file, pressing Control S. Right, and then if we try to compile again, hopefully it should. I think we made some error here. What is it saying? Oh, okay. So I think I reversed the order here. It's actually info and then device name. Hopefully this should work. So you can see that it compiled. So now if I try to run this code, you'll see that it's actually printing out the device name. And then it's also printing out the output value, which is 3. Okay. So this is running on the Xeon Gold CPU. So let's say if we want to run it on one of the Intel GPUs, right? So the way we run, so this Intel Dev Cloud has a bunch of different systems with different types of GPUs and different types of CPUs. So we've written a script that will use QSub to submit your compile script to any system and execute it there. Or what you can do is like you can log into a system which has a GPU and then execute it there. So let me actually, before I do that, let me print this one line that I added to the source, right? So copy this to the chat window in case somebody is trying to do the same thing. Okay, I think I see a question here. Somebody's asking for, I missed the initial part of the meeting. Can someone point me in the direction of any document to follow the steps? So I think to get all this material, just go to this link right here, the devcloud.intel.com, sign up for an account, and then this tutorial should be okay, so that's the link to get into DevCloud. So once you've logged into DevCloud, use this copy command, right? CP-R and copy the workshop contents, and then you'll have access to it. So if you have any issues, just type in a message again, and we'll help you there. Right. So the next step is, so let's say we run it on a CPU. Let's see if we have to run this on a GPU. So we have to log into a system with get the command to so I think, let me try this Q. So, so what I did was I ran this command in my terminal. Right, so if you run this command in the terminal, what it will do is it will go and find a free node which has a GPU in it. Right, so you see that the login actually changed. I was on this node N059, or they changed me to a different node. So now if I do a CL info -L, you will see that this particular system has a different Intel processor, which is a Gen 11 generation core CPU, and then it also has a graphics card, integrated graphics card. I believe this is Gen 12, I think, right? So you can again go into the same directory, and then we were in DTCP output directory, right? So if you go here, and then you can try to run the same output binary. So if you run this here, you can see that it just ran it on a graphics device instead of running on the CPU, right? So now if I exit out of this node, I just type in exit, and then now I'm back to my original node. If I do a CL info -L here, you can see that this node does not have a GPU, right? So if I run the command here, it runs on the CPU because there is no GPU, right? So now so that way you can actually change different machines and then run the same code, and it runs on the device that's present in that system, right? So you can also use this command. So we use this qsub command, right? So we are just specifying this option as GPU, which means that just find any GPU, right, on the dev cloud. So if you want, you can specify actual parameter, like if you say Gen 9, for example. So this will go and find the Gen 9 node on Intel dev cloud, right? So there are hundreds of nodes. So all of you should be able to get one of these GPUs to test, right? So now if you do a CL info -L here, you can see that it has a different graphics device, right? It has this graphics P630, and then this one has a Xeon processor. So now again, we can go into your working directory, dpct, and then we have a a.out file there. So let's run that here. And here again, you can see that now it actually ran on the graphics device, right? So you can see how SYCL code is capable of running on any kind of device, right? Whether we saw it run on an NVIDIA GPU, we are seeing it run on Intel GPU, and also on Intel CPUs, right? So that's the main goal of SYCLomatic, is mainly to migrate CUDA source to SYCL, so that you can now take this source code and then run it on any hardware from any vendor and any architecture you want, right? So it gives you portability to run the same SYCL code everywhere, right? So that's the main advantage. And then so this is just demonstrating that. So we used a very simple code to do all the end-to-end functionality. So the next step is like, let's look at how do we handle much larger CUDA projects, right? So this was just a hello world that we looked at. So we looked at this CUDA source, which is only about like 50 lines of code, one of the simplest CUDA code you can write, right? So we can see how the SYCLomatic tool will actually migrate when we have large projects with multiple CUDA files, kernel code, and the host code separated, and so on, right? So that's the next step. So let me know if you have any questions so far, if you want me to explain anything more. If not, I will jump back to my CUDA machine here, and then share some more tips here, right? So you can see that we have the CUDA source here, test.cu, right? So to recap, what we did was we just did C2S, and then we just did test.cu, right? So usually if you try to run it again, it'll say that the directory is not empty, right? So if you can try to run it again, you can see that it gives you an output that the dpct output directory is not empty, right? So if you want to run it again, either you can go in and then remove. So these are just tips, right? You might run into these errors. So just remove the file, and then you can run it again. And then now it will actually migrate and then create the same dpct output, right? So if you want to create the output in a different folder name, you can do that too. So there's a command line option. So we can say the command line option is called out root, right? And then you can specify a folder name. Let's call it SYCL, right? SYCL code or something like that. And if you do that, so the main difference is I just created a folder called SYCL code, right? And then inside that SYCL code, it generates the SYCL code, right? So if you want to look at more options for command line options, we can just do -- help, and then this will show you all the different options. So there are cases where if you're including multiple files, you can, there are different options, and then a lot of features, right? Depending on how you want the style of code, right? The SYCL code that is generated, if you want it in a certain format, tab space, and all that stuff. So you have a lot of option to change that. Okay, so with that, next, what we will do is, so we will migrate slightly more complex code, right? So this is what we looked at right now is just a single source file. So let me check. I think there's a question here. Where is the CUDA to SYCL directory on Python? I cannot find it. Okay. So this, I'll paste oh, wait. So in your terminal, you have to open the terminal in DevCloud, and then can't I paste this one? Okay. Hold on one second. So if you run this command that I just pasted in the chat window, you will be able to copy the whole tutorial files, right? So all the source code is available inside the directory. So wherever you copy that, if you're by default, you'll be in your home folder. If you run this command, this folder called CUDA to SYCL migration will be copied. And then inside that, you'll find 4 different directories, and then you can go through the tutorial. So hopefully this helps. Let me know if you have any more questions there. Okay, so next what we'll do is we'll get a more complex CUDA source. To do that, what we'll do is we'll look at some sample code that's in the NVIDIA CUDA samples repository, right? So let's look at the CUDA repository. So here's the link to the CUDA repository that we'll be using. So I just pasted that in the chat window. So what we'll do is we'll clone this repo, right? So I'll copy this link, and then I'll go back to my CUDA development box, and then we'll just do a git clone. This one. And then this should pull down the entire repository, right? So I think there are, about 150 different CUDA examples in this repository, right? All using different kind of CUDA features. So, and most of these are not very simple projects. It's implementing like actual algorithms using like 5 or 6 CUDA files and a bunch of other support files, right? So it's more of a real world project. So we'll be looking at this one. So let's look at what this downloaded. So CUDA samples is the directory. So let me go into that directory. And then I have a samples. So let me go into samples directory. And here we can see that we have different folders here: introduction, concepts, and techniques. And one of the sample I want to try out is it's in the concept and techniques directory. And there is a folder called sorting networks, right? Let's access that one, sorting networks. And then if you look at the files in that, you'll see that this project has a bunch of different files, right? So it has a CU file here. It has a main.cpp, right? It has odd even merge sort.cu, and it has another bunch of sorting networks common file. It has a validation in another file. So it's quite a complex file, right? And then it has a lot of dependencies on a lot of other common files. So if you want to browse this project, so let's look at main.cpp. Right. So you can see that it's including this CUDA runtime, which is part of the CUDA XDK, and then it also is including some utilities and system include files like helper underscore CUDA, helper underscore timer, and then including this sorting network common.h, right? So what do we do when we have multiple files, right? So that's our challenge here. So one of the way we can automatically track down all the files used in the project and then migrate all the related files is by using this command called intercept build, because since this has a make file, this make file will have data about all the different files that are compiled and all the other dependencies within the make file, right? So this tool will just go in and then create a JSON file of all the files that need to be migrated. So to do that, what we'll do is we'll run this command, intercept build. So this is also installed as part of SYCLomatic in the bin directory. So if you've added that to the path, you should be able to access that anywhere. So intercept build, and then just type in make, right? So if you run this command, you'll see that it did a bunch of things, right? And then it actually creates, let's check the folder here, and you can see that it created a file called compile underscore commands.json, right? So let's look at that file. If you look at this file, it's just a list of all the different CUDA files, right? So that is one of your source, main.cpp is your other source, or even merge.sort is your other source, right? So it just creates a list of all the files that is in the project. So once you have that, now you can migrate all of those in one shot by just specifying this JSON file. Another thing is that you notice that the main.cpp file was also using these CUDA helper files, right? Helper underscore CUDA. So let's look at where that is, right? So if you actually go back like 3 folders down, you'll see that there is a common folder, right? And then you have all your helper files right here that's used for these sample projects, right? So this particular project is actually using this helper underscore CUDA, and then it's using helper underscore timer, all these files, right? So if you want to include all these files, so there is a way you can specify this SYCLomatic tool. You just do C2S. You use this -b option to specify the compile commands.json. So this will give you the list of all the project files, and then you can actually specify the actual input path where it looks for all the other common files, right? So you can just do // and your common is actually right there, right? So you can just specify 3 levels back, right? So now if you actually run this command, you'll see that it migrates a bunch of different files, right? And then if you just browse the directory, you'll see that it has created this dpct output. So let's go into dpct output. And inside this, you'll see that again, it maintains the same directory tree, right? There is a common, and then there's a samples folder. So let's look at what's in common. It has a subset of what was in the main common file, right? So these are all the files that this particular project is using. So all those files are being migrated, and that's also copied here, right? And then we have samples, and then we have the sorting network, right? So it has migrated a bunch of these CUDA files, which used to be .cu files, now has been changed to .dp.cpp. That means that this is one of the migrated file. We had main.cpp, which is changed to my main.cpp, dp.cpp, right? It changes the names. So this is your actual project file. So now you should be able to just compile this one as it is, right? So if you want to compile this, so let's get into this directory, samples, sorting network, right? So how do we compile this? Just use the same command again, icpx. So you may not be able to compile this if you haven't installed the Intel compiler, but if you have installed it, all you can do is like just input to SYCL and then specify the include path, which is 3 directories back, and then there's a common, right? And then you can just say startup CPP. So it just compiles all the CPP files that you see in this directory, which is all these files. And then plus it, we are including all the dependencies here in the common folder. So if you run this command, there you can see we are seeing some warnings generated. So let's see if it compiles. So a couple of warnings, but then we don't see any errors, right? So which means that this is good to go. And you can see that it has created your output file. So we can try this one out, right? So it's doing some sorting algorithm, and you can see that it's basically printing out the total average time here, throughput, work group size, and so on, right? So this is a SYCL code compiling, and we are seeing the result, right? So if you want to compare it with I didn't actually show compiling for NVIDIA, so you can actually do that too, right? So if you go back to the original CUDA source path, so here's all my CUDA source, so we can do a make clean, and then make, I think. Okay. So this one, I've noticed that you have to slightly modify the make file to run it here because it has it doesn't support the Compute 90 architecture. So if you want to compile on NVIDIA, so you have to just go ahead and delete this 90. And then you should be able to build it for your NVIDIA machine. So just do a make run. Right, so pretty much somewhat similar result, right? It basically says that its values are okay, inspecting key arrays, and then just printing out some throughput values, and then average time, and so on. So the same code, CUDA code, we migrated to SYCL, and then we are able to compile it, right? So this project too, if you go, if you don't have a CUDA machine and weren't able to follow this one, so you can always go to your dev cloud, and then let me. So if you go back to your project here, you can see that we have 4 folders, right? So the project that we just did was the sorting networks. So access this sorting networks, and then you can see that we have a Jupyter notebook file. And inside this Jupyter notebook file, we have documentation again showing how to install SYCLomatic and how to use the tool and so on. And then this actually describes what this project is about. So we have the main .cpp, which has the host site code, which mainly identifies the GPU device, does memory allocation on the GPU, initializes the data on CPU, and then copying the data from host to GPU memory, and then it kicks off the computation. And all the computation is done in these 2 files, which is mainly defines a kernel, allocates some shared local memory, and it does the Audubon Mozart computation, right? So, and then you have all the commands here. If you want, you can try out all these commands on to migrate this code and then run it on different CPUs and GPUs, right? But if you want to access the output, DPCT output folder, so this is the migrated code, so you can do a quick comparison, right? So let's focus on doing that one. So here's the set of migrated code. And then let's compare this with the NVIDIA code, right? So what I'll do is like I'll try to get this side by side. So the product that we accessed is sorting networks, which is right here. So let's click on main.cpp, and then here we'll also access the migrated file, right? So now we can do like a side-by-side comparison. So you can see that when the file is migrated, it tries to keep all the comments intact, right? So you can see that the first line of code is on line 42, which is mainly include CUDA runtime. And if you look at the migrated source here, you can see that instead of having the CUDA runtime, now it's being replaced by SYCL/SYCL.cp HPP, right? And you can see that it's also including what's called DPCT.hpp, right? So this is just helper function that the tool, SYCLomatic tool has. SYCLomatic tool itself used to be called DPCT before. That's why we see the reference to DPCT everywhere. So this mainly has wrapper functions, which makes it easy during migration, right? So that's what this is. And you can see that it keeps the other helper files intact, right? helper_CUDA. But then these helper_CUDA files are also migrated, right? So, and then same thing with the other header file too. So it keeps all the header files as it is, but then the contents of the header file may not be the same, right? Because those are also migrated. So let's look at the first series of lines of code here, right? So if it's just C++ code, then you won't see any difference, right? So C++ is the same. So you can see that all the mallocs and the malloc here are the same. So where you'll start seeing the difference is mainly when we start doing some actual CUDA APIs, right? So here you can see that on line 82 here, you can see that we start by allocating memory on the device using CUDA malloc. And here you can see that that CUDA malloc is now being replaced with malloc_device. And usually when the migration is done, if there is anything important you need to check, the tool actually creates like comments called warning comments, right? It mainly gives you migrated API does not return error code. You may need to rewrite the code, right? It's mainly, it's not a major error, but it's just saying that it may not, in CUDA, I guess it returns error code, but in SYCL, it may not return error code. So if you're dependent on that, it's just saying that you may not get the right error code, right? So this is not something major, but the code is still compiling, so we don't have to worry about it at this point, right? So you can see there's a bunch of CUDA malloc, and all those are migrated to malloc_device, right? And then we start seeing CUDA memcopy, right? So that CUDA memcopy is now migrated to the queue.memcopy. So this is the SYCL equivalent of copying memory from one location to another location, right? From host to device or device back to the host. And once we've done that, so let's look at the other any other CUDA APIs. So on line 105 in CUDA code, you can see that we have a CUDA device synchronized, right? So the equivalent of that is actually there's a get current device queue wait and throw, right? So this will actually synchronize once synchronized. Mainly, this will make sure that it will wait until all the mem copy is complete, right? So that's what basically this CUDA device synchronize does, and then queue.wait actually does the same thing in SYCL. Okay. So let's keep scrolling down. You can see that again, this is all just C++ code. We have more mem copy that's being happening here, and then we have freeing the allocations at the very bottom here, right? So you can see that in case of SYCL code, instead of doing CUDA free, it's doing a SYCL free, right? Everything else is the same. And then from this main file, shut up this one. So from this main file, you can see that we are actually calling in the actual kernel function, which is validate sorted keys or validate values. So these are the main functions that will do the kernel operation, right? So next, if we want to compare, let's say, for example, we have the odd even merge start.cu. So this looks like an actual file that so that's odd even start. So these two files, right? So on the left, you see the CUDA file. So here you can see that again, in case of SYCL, we're including the SYCL header files, and the other helper header files are included as it is, but just notice the difference here, right? In case of CUDA, we included sorting networks underscore common.cuh, right? This will be automatically changed to .dp.hpp, right? Because that is the migrated code. So the tool itself will take care of all the details like this. So you don't have to worry about all the included files and all the other helper functions that you are using. So let's go into this kernel function, right? So in CUDA, we define it by saying global and then audio merge sort shared. So you can see that we have a similar function in SYCL on the right here. You can see that here we are using CUDA, we are using the thread block. So you might be familiar with this, right? So we are specifying the thread block, which is same as workgroup in case of SYCL. So we are defining the similar variable CTA, and we get that by doing item.getGroup, right? So SYCLomatic will automatically change these functions and methods to use the SYCL equivalent of that, right? So on here, in case of CUDA, you see that on line 49 and 50, we are using shared local memory, right? In case of SYCL, we actually define that in the kernel definition, which is defined when there is a kernel is defined using parallel for, right? And we use q.submit. So that's the main difference there. And you can see that whenever the actual logic, instead of using the block index, here we actually end up using get local ID, right? So the block index is mainly the get group, and then thread index is get local ID. So you see that all those are migrated. So if we keep scrolling down, notice that in CUDA code we use the sync functionality mainly to synchronize all the threads. And here, in case of SYCL, we use barrier function, right? You can see that we use item.barrier. So similarly, you can see that yeah, all the CUDA APIs are actually migrated automatically to SYCL APIs. And if there is anything that needs your attention, you'll see comments being generated by the SYCLomatic tool. It just gives you tips in some cases, right, to improve the performance. So for example, here, you notice that it's saying consider replacing SYCL ND item barrier with ND item barrier, and then specify that it's the pen space is actually local space, right, for better performance. So it gives you tips like this. If this barrier is only needed for local group, then you can specify it this way, but by default, it will just create a barrier which may not be the most efficient one. This is something you need to analyze the code and then see if there's any performance improvement you'll get by doing the suggested comment. Right? So the rest of the code, you can see that it's mainly the main difference is the block index and thread index are being migrated to get group and then get local range. Yeah, so you can see there's a lot more comments here, right? So mainly this is saying, so another important warning, right? So the workgroup size that's used in the CUDA code is actually fixed to a certain value, right? So depending on which GPU or CPU you're running, each device has its own maximum workgroup size. So this is just asking you to query for max workgroup size and then set the workgroup size to whatever is appropriate, right? Otherwise, you might get an exception when you try to run the code, right? So even the shared memory size depends from device to device, right? So the CUDA code that you get might be written to a specific device, and it may support a specific maximum size, right? So in case of migration, those are the things you need to pay attention to. And the migrated code will actually give you comments wherever you're using that, just as a warning, so that you pay extra attention to actually change this, right? So in this case, you can see that the local memory is created in SYCL by using this local accessor command. And then it's setting as 1024. It's just giving you a warning saying that, okay, it's the shared size limit, right? It really depends on the shared size limit. If 1024 is not the right value, you might have to readjust it, or depending on the hardware, right? Yeah, so the rest of the code, you can see that it's similar comments here. So that's just the overview of. Okay, let's let me go full screen on this one. So now that we've analyzed some of the migrated code, let's try to compile it on the dev cloud, right? So you can also follow along and do the same thing. So let's see what I have in the directory. So mainly the code we are trying to compile now is the second one, which is 02. So cd into that one, SYCL migration sorting networks, and inside that you'll see that you have a dpct output folder, and you'll see that this folder has a samples and then a common file, right? So your actual source is inside the samples directory. So let's cd samples and then sorting networks, and then that's where you have your source files. So if you want to compile this, we'll do icpx -f SYCL, and then I'll specify the include path for the common files, right? And then I will just do star.cpp, right? So to compile all the C++ files that are in the directory, which are all these files, right? So this is the compile command. So again, you see that there's some warning saying that one of the expression is unused. So you can, if you want to get rid of that warning, you can go and fix that one. But looks like we are not seeing any errors. So it should have generated a binary, right? So then we can run this file, and you can see that we are getting an output, right? So well, again, in this case, right, if you want, we can modify the code so that it prints out which device it's actually running on, right? Because it looks like, so let's go into main.cpp, and that's where I think we are creating the queue. I'm trying to find the okay, so what we can do is right up top somewhere. Go to device. Maybe right here. We can add the same line that we added, but slightly modify that. But we don't have a q.cd1, but I think the way they're doing it is using ppctq.default q.get device. Let's try this one. Right, so now if I run a.out, and if we scroll all the way to the top, somewhere in there, yeah. So now it's printing out the device it was run on, right? So now you can see that this code was actually compiled and then was executed on a Xeon device. So let's go back and then change your node to a GPU node. Right, so where is that? Okay. So let's queues. That's capital I, that's I. Hold on 1 second. I'll try to find the command here. So let's try to run this on, I think we have a Gen 11 device. SYCL, I think. So mainly what we did was using this command, we requested a node with the Gen 11 device. So let me paste that here for people who want to try that. All right, so now if I do CL info -L, you'll see that this node actually has a Gen 11 graphics device, and it also has a 11 generation Intel Core CPU. So let's go into CUDA migration 02 PPCP folder, and then this folder should have a, oh no, not this folder, but you'll see that we have the output file right here, so we can directly try to run that and see if we can see the output. You can see that it completed running. Then let's scroll up top and then see which device this was actually executed on. So here you can see that it was executed on previous occasion. It ran on the Xeon device, and this occasion it actually ran on the Core, which is what the system that we logged into, right? So let's go back to chat window. I saw that there was 2 more questions here. Okay, so one of the questions is, will intercept build work with build files generated with CMake? So I haven't tried it. So if there was a CMake project that I tried, which ended up generating a make file, right? And then you can use the CMake and space make, right? Yeah, so your project should have a make file. If not, you can also migrate each file one by one, right? So how can I target an Intel GPU with ICPX? Or do I need a plan for that? So yeah, so you don't really need to target using ICPX for Intel GPU, right? So so when you create the queue, right? So let me go back to this vector add example. So by default, you know, when you create a SYCL queue, right? Let's say we create a SYCL queue like this. This means that it's a default queue, which means that it will pick a GPU if it's available, right? If there is no GPU available, it will fall back to a CPU. If you specifically only want to run on a GPU device, then you can specify something like this. You can say SYCL device, no, say GPU selector _v, right? So if you run a command like this code will always run on a GPU. But if you try to run this on a system that does not have a GPU, then you'll get an exception, right? So if you want, we can actually try this one, right? So the queue has been created using these commands, right? Using the wrapper function. But under the hood, what it's actually doing is basically creating this same command. So what we can do is just comment out this one, and then you should be able to, let's use the same variable, right? Q_CT1. So let's try this one. Okay, so we can do just ICPX, SYCL, and then let's try this one. Now, if I run this one, you can see that since I said run it on a GPU, it ran on a GPU. So you actually target the devices in your SYCL code, right? Not actually using the compiler. So if you want to change this one to, let's say, instead of saying CPU, GPU selector, you change that to CPU selector. And then we can compile this again. And then do a.out. And now you can see that it actually ran it on what do you call Intel Core device, but you see that the output is not correct, right? So that's probably because I know we are supposed to use in order Q property for this one. So property. I think that is the, let's try this code. Right, so now you can see that you get the right output, but now since we specifically said run it on a CPU, it ran on a CPU, right? So again, what I did was I added in order Q property. So this is something when you say create a queue using default, this actually under the hood, it's actually creating this line of code, right? But then if you're not sure, if you try to run this code with GPU, for example, right? If I say GPU and let me compile this again just to show you what happens if you try to run this on a system with no GPU, right? So now the system has a GPU, so that's why it just ran it on a GPU. So let me exit out of this. Right, so now let me go into right? So let's look at CL info again on this system. So I went back to my original node, which does not have a, oh no, this one has a GPU. So let me exit out of this one as well. All right, so now let me do CL info -L. So now you can see that this system just has a CPU, doesn't have a GPU. But if you force your code to actually use a GPU, so you will get a device not found exception, right? So that's why it's not recommended to use a specific GPU or CPU selector. So what you can do is like just say default selector, right? So default is the safest one to use because it will try to find a GPU, and if you don't have a GPU, it will fall back and run on the CPU, right? So let's compile this one. Okay, ICPX. A.out. So now, since we've used default selector, it did not find a GPU, but instead it found a CPU, so it ran on a CPU, right? So that's why in most of the code, you'll see that people specify default selector. Another way to ask it to select default selector is just not put anything, right? By default, if you don't add anything in there, that also means that it's using default selector. So we can compile this and try. Right, so you can see that it ran on the CPU. So hopefully that answers that question. How can I target Intel GPU with ICPX? So you cannot using ICPX, but rather you're just specifying in the SYCL code itself. So, so the main difference, right? ICPX is mainly the compiler that you get from Intel base toolkit, Intel One API base toolkit. It's mainly for Intel devices. For any other device, we mainly use CLang, right? Which is the CLang++, but both will be using the same SYCL compiler, right? When you're targeting NVIDIA, we use CLang and we specify the SYCL target, right? So that's about what I had for today's workshop, right? So one last thing that I wanted to talk about is, once you migrated both of these examples, we noticed that we just ran the tool and it migrated the code completely, and we were able to run it on the device. So this does not really mean that the code that it generates is efficient and more performant code. So you do have to take measures to actually analyze the code and then write a more efficient code, right? So let's look at this simple vector add example, right? So it's a very small code, but let's look at if there's any efficiencies we can change, right? So I just told you that by default, when the SYCL code is when the CUDA code is migrated to SYCL, the queue that is created always creates using this property called in-order queue property, right? So what does this in-order queue property means is that all the kernel functions are executed one after the other, right? So what are all the kernel functions here? So memcopy is something that is run on the kernel, right, to do a memcopy, and then we have two memcopies, and then we have the actual kernel computation using parallel for, and then we have memcopy. So when we use in-order queue property, so it actually executes all of these four kernel calls one after the other, right? Even if there is no dependency between the four kernels, it actually executes one after the other. This is mainly because the tool wants to make sure that you get functionally correct results. Mainly if you try to overlap kernels, it may be prone to a lot of errors, right? But in some cases, if there is no dependency, you should actually let it overlap, right? So that you get the best performance out of that. So the first thing you may have to do if you want to improve the performance of this code is get rid of this in-order queue property, right? So instead of having this property, you get rid of it. So now what happens is that all the queues actually, all the tasks will execute, will be submitted at the same time, and it can overlap. But the problem is some of these have dependencies. So you have to manually set dependencies between the kernels. So let's analyze this, right? So the first two, we have two memcopies, right? And there is no dependency between these two. Each of them is doing independent memory copies, right? A is copied to D underscore A and B is copied to D underscore B, right? So these two can actually execute concurrently. So which is, so that's why we could just remove this wait. Now these two will be executed concurrently, so will this one also, right? But then in reality, we should actually wait until the memory copy is complete and then start executing the third kernel. And same thing with the memory copy, the final memory copy, right? They should only be copied after the execution is complete. So how do we add dependencies for it, right? So you'll have to manually add set an event. Let's call this E1, right? And call this E2. And then in the parallel for here, we can actually say have a dependency here, right? So you can say E1 comma E2, right? So if we do this, we specify the two events in the parallel for kernel here, it means that this execution of this kernel should actually wait until both these events are complete, which is both of these events, right? Both the mem copies. These two will concurrently be copied, but then it should actually wait for this one. And same thing with this one, we should have a dependency for executing this mem copy, right? So what you can do is like add a auto E3 here, and then right at the end of this one, just add a E3, which means that this mem copy will not start until this computation is complete, right? So now what we've done is we've taken the migrated code and then we've optimized it so that there is some concurrent kernel execution allowed, right? So this is actually better than the migrated code. So let's see whether there are any errors or if this code is working correctly. Right, so let me run this one so you can see that it ran the code. So if you take a much larger code, right? And then if you add timers to it, so you can actually see some performance gains, right? So this is just showing a simple example where we've taken the migrated code and then did some optimization to get better performance, right? So same with the other project that we just migrated, the sorting network, right? So it's always good to go through each one of these lines where the SYCLomatic has added comments and then see if there's any performance improvements that you can do, right? As it is out of the box, the code that is generated will probably give you functional correctness, but then to get performance, you still have to do the work of optimizing. Okay, so with that, we are done with today's session. So let me know if you have any questions or if you want me to explain anything else.